All right. Took me a few extra minutes getting ready today. That's okay. I put up the due dates on the board of everything that's coming down the pipe. Labs are still being negotiated amongst us as to when things are actually due. But I think things are settling down a little bit. Howard's running a little behind Kamari. So he's trying to catch up and Kamari's trying to slow down. So, you know, so the next week should settle things down fairly well. Assignment 2 is due November 17th. As you notice here, there's a drop dead date. I guess I never had a chance to explain to you guys the concept of due versus drop dead. Due means that's when it's due. Drop dead means after this date I give you a 0. It's pretty simple. If you're after this but before this, you take a 10% hit.
Every day or in total?
No, it's too much work for me to calculate. Like, really? I just take 10% off. So if it's out of 35 points, you lose 3.5 points right off the top before you even start grading. It's pretty straightforward. I mean, if I did 10% a day, that's 7 days. You'd end up with 70% off. There's no point doing it.
That's true.
So drop dead, November 24th. Hybrids, have them done on or before the 24th. Because they prep you for the test that you get on November 24th to the 27th. It's like same deal as last test. So it's 3, 4, 5, 6, and 7. 6 and 7 shouldn't be killers. Chapters 6 and 7 are actually pretty straightforward in the book compared to everything up to that point. Test 2, November 24th to 27th. And as I put down a question mark next to the labs, I've told Kamari to hold off on lab 10, and Howard's not ready for lab 10. Because unless you've got the lecture to go with lab 10, you're not going to have a good time. Just putting it out there, it's not going to be a good time. Yeah.
Does that mean
Yeah, that one's going to be pushed further down. Also, there was some confusion as to when your practical in-lab assessment was going to happen. I don't know if it actually trickled down to you guys or not yet. I've straightened out Kamari significantly, and Howard breathed a sigh of relief when I said it. Actually, the in-class practical happens the week before the final exam. That's literally, it's all in the labs. There is no lab work that week. You come into your lab, you do your practical, done. That same week will be the review. Or even the review might even happen before that, depending on how well we do with the content. What other information you need to know? I've had one person ask me, I don't remember from what group, as to how long is the final exam in case you need to book at Cal, and it's 2 hours. So it's a 2-hour multiple guest scan shot job. I'll cover the exact topic that's on it during the review, just so that you know what to target when you're studying. What are we covering today? We're covering 2 sets of topics. And as after today, the 2 groups are almost synchronized. They have a few things less than you guys have a few things more than them, but really you're almost at the same point now, which is good. But what you're going to cover today is I'm covering unions, intersect and accept, which is set operations, and then I'm covering performance tuning, as in when you're planning your content. And hopefully I don't make as much of a dog's breakfast out of that part of the lecture as I did on Monday, because I pooched that lecture completely. I lost track of what I was doing, and it was really loud out in the hall, and I lost track halfway through the lecture of what I was talking about. It was pretty bad. I swear I was on some good drugs or something at that point. It's like, gone. But yeah, that's the plan for today. If it all goes well, actually the lecture will finish early, so everybody can go have supper early, or go home early, or whatever, if it goes well. And that means that if we finish, it's going to be a little quick. The guys on Monday got the exact same lecture as you guys, except they had a little extra stuff at the beginning that you guys have already had. Therefore, at this point, we're essentially, I'd say you're 97% at the same place as the other group, which is actually going to go really well going forward, because then it's the same lecture for everyone. And it's the same work for everyone. But you guys get the polished version because they get the practice version on Mondays.
That was a close call.
Now my tripod's pretty stable. We're going to move it over a little bit though from your feet.
Yeah.
All right. So, I'm going to do this. Actually, I'm going to stick to the board for a minute, since I have just so much whiteboard. Everybody got the dates that they need off of this before I start erasing?
Yep.
We're good? Okay.
Sorry,
Actually, yeah.
are any of these dates on Blackboard by any chance? Or?
The assignment due date is on Blackboard. The hybrids I got to push in, and the test. The problems with the way they do the dates is it shows you when it's actually dead due, not. So, for example, the test is from the 24th to the 27th. It would show you the 27th, not the fact that it opens on the 24th.
But all of these are one way or another going on Blackboard.
Yeah, I just got to update your hybrids because I was trying to calculate exactly when you guys should have your test compared to the other guys because they're getting it next week. So, you guys are rolling a week behind them.
What about the drop dead under November 17th?
November 17th. This assignment is due on the 17th. You get full marks to get it in before midnight on the 17th. If you're past the 17th, but before midnight on the 24th, you get your grades minus 10%. After this, you get goose egg. Absolute zero. And I love that grading. It's like 0, enter, because I just sort, right? Sort by not submitted, 0, enter, 0, enter, 0, enter. It's really quick. It saves me all kinds of money. All right. Anything else before I erase so I can use the whiteboard? Okay, we're good. All right. How many of you remember Venn diagrams?
Yes.
All right. Venn diagrams are designed to explain how set operations work, or at least how sets work. And essentially, that's the best way to explain set operations with databases. I got really no whiteboard at all. Okay. When you think about the database, and there's 3 common set operations that apply to mathematics outside of database. There's the union. There's the intersect. And then there's the except, which is also known as minus. Depending on what database server you're talking about, the except and in minus means the same thing. I really wish my circle drawing skills were better, but they'll do. Okay. I'll be doing some demos on the screen once I've explained the basic concepts. So the way set operations work in a database server is you take query A, then you take query B and you apply the operator between them. So you take query A, you do a union to query B, and then you get a result. Now, do you guys remember what a union is for sets? Remember, did anybody here take sets in high school? Set math? Some of us are older and remember sets. Some of us that don't come from Canada probably know sets. Apparently, Canadian education system doesn't cover set operations in high school anymore. Basically, sets operations means you take one set of data and you compare it to another set of data, and you end up with a result on the other side. The union operator means it grabs everything from set A, plus anything it finds in B that is unique. So you end up with a partial B. When I do the demo on the screen, it will make more sense. But that is a union. It's actually everything from A plus any unique values of B. So what the union does, unions, I didn't give myself a lot of room. Union Unions give you the distinct values of both sets put together. That's the purpose of a union. Now, the next one is the intercept. And I'm going to write down here. Intercept. Intercept gives you what exists in both sets only. Not sure what word I was writing there. So intercept, I don't know why I wrote intercept. It's the same thing as intercept. Intercept and intercepts are actually the same thing. Okay? It gives you this. Can anybody guess what the minus does? So it gives you everything from minus, or except, gives you everything from A minus anything that I might find in B. Also known as minus. And to draw it up on the board, that's the minus. I'll give you guys a colorized legend. Okay, so those are the bits and pieces of what the set operations do. This is typical math. I don't remember which branch of math it is, but it's math. Now, when you deal with the database server, there is a small difference though. And something's gone tight. All right, when you work with sets, there's 3 rules. And in most database servers, all 3 rules apply, unless you're working with MySQL, because MySQL is special. Rule number 1. Both sets must have the same number of columns in the query. In other words, if you select 2 columns in the first query, the second query must have 2 columns also. Otherwise, you're comparing to similar sets, which you cannot do set operations on because they're not the same. Rule number 2. You need to have similar data types. I don't mean from one column to the next, from one set to the other set. So if column 1 is a number in set A, column 1 in set B should also be a number of some sort. Now, normally it's okay if you're mixing numerics and integers because they're both numbers. What it doesn't like is when you start mixing text and numbers. Okay, this one applies to 50% of database servers that I've experienced. I'm going from practical experience here, not, you know, written down rule. MySQL doesn't care. Last time I used Oracle, it tried to thunk. In other words, it started casting the data types from one type to another type, trying to make things work. And we can all imagine how well that actually works. It doesn't. Postgres cares a lot. Microsoft SQL Server cares a lot. SAP DB cares a lot. DB2, I have no idea because I've never worked with it. 3. Columns must have the same name. This one applies to about 90% of the database servers out there. If they don't have the same name, use an alias. In other words, you rename the column in one of the queries. I'll just show you guys when I do the demo what happens. All right. Those are the 3 rules. Now, there's a thing that's not quite a rule, but it's a gotcha. All right? I'm going to put down this question mark because it's a gotcha. It's not really a rule. The more columns you have, the more distinct the data is. By that I mean, if you include the primary key in the union operation, every single row is unique because the primary key is included for the right. That means the union will give you back absolutely everything instead of just 1 or 2 things. Okay. Those are the rules. Now I'm going to do some demo. And that'll make things go a little clearer.
Is union everything except for intersect?
No, union is everything from table A plus anything that's unique in table B. Intersect is what exists in both tables or both data sets identically, and except is everything that's in table A that does not exist in table B. So those are the 3 common. There's a few others that have been known to crop up over the years. XOR is one, for example. Is it great? No, but it does the job. It's just one of those things. All right. Let there be Postgres. All right. So, for those of you that have started or have seen Lab 9, there's a point where it tells you to import another database file. Those that haven't started Lab 9, you haven't seen this database file yet. Essentially, what I'm going to be doing on the screen is practically part of that lab, just so you know. So this is when you might want to bookmark in your brains to come back and watch this if you get stuck in the lab. So if I grab email from customers, this is in ThinkCube as usual. So we get the email addresses from the customers with 10,000 rows. Now there's another table I've created in there called Trade Show Leads, and it's got 1,300 rows. I'm actually going to write the numbers down over here so you guys can visualize a little bit better. $1,329. All right. So if I were to grab, I'm going to switch this back to what it was before, which is customers. Now I'm going to do the union. Now, if everything was unique in both tables, we should end up with 11,400 and change. However, when I crafted this data, I made sure there was some duplication. So I end up with 10,964. That's the union. That is the unique email addresses from table A and table B. Now, one of the common uses for this is if you're trying to establish a clean list of data. For example, a while back we had a customer, one of our competitors went under and they sold us their customer list as a way to help pay off their debts. They sold us their customers, it's great. But what we had to do is we had to figure out which ones of those people were already our customers also versus customers we've never seen before. So we ended up with a list of email addresses and phone numbers and that kind of stuff. And I spent a couple of days running various union and intersects and that kind of stuff. Now, what I wanted first was the marketing guy wanted a distinct list of email addresses. I ran a query that looks pretty much just like that. Give me all the email addresses from one, union all the email addresses from the other, and it gives you all the distinct values from both sets. Boom. So right after that, the guy said, okay, now we're going to run a special promo for cross customers where they existed in both systems. So I literally took the same query and I went intersect. And this should give me, actually, if I take those two numbers and add them up, subtract that number, is what this should give me, 459. So in both lists, customers and the trade show leads, I have 459 that already exist side by side. Which was good, because it allows us to find the ones that are in both places. That means we can probably clean out one list, or maybe we want to use that to update another list, that kind of stuff. That's what intersect does. It gives you the matches from both. And then you can do the except. So in theory, what we should get is 10,100 minus 459, which gives us 9,600 and change, which is 10,000 minus 400 and whatever. And that's the except. Literally, that's all there is to unions and set operations. As long as you remember to have distinctness between the two lists, it works. And as long as you follow those rules I put up on the board, it'll work great. So I'll do the union one more time, just show you what happens when you.
Is that 10,100?
Yep. Yeah, that's 10,100. That's a 1. My horrifyingly bad handwriting. And I lost my mouse. Come on. There it is.
Because it doesn't matter.
Yeah, it does.
459.
Yeah. There's 459 between the two, they're the same. So you take 459,
Minus 10,100.
yeah, 10,100 minus 459 will give you whatever number, 9,000 and change. Okay, so this is a standard union. Now, if I were to go and grab, let's just need to pull something up here on my screen for a second. Okay, so let's just say we want to go grab and throw in the name on there for fun at the start of my set operation. Now we got 10,973. The number changed just a hair. Why? Because some of the names are a little different. If I were to throw in the ID instead, that means that everything should be unique. Theoretically, I should end up with 11,429, which is actually the two lists added up together. Ish. There are some duplicates in there because I made sure there was. Yes?
Where do we get the additional part of the database?
Um,
Query ours for trade show, it doesn't exist.
Yeah, because you need to import it as part of Lab 9.
But where do we get the SQL file to help import
The
it?
backup file was given to the lab monitors. If not, I will email it to everybody.
That would be great.
Because if it's not there, no? Okay. Send an email. All student users. Trade show leads. Attach file. Ooh, loud. There it is. Browse. Restore into hey, it's a backup file. I just emailed it to everyone. There, done.
So we just import that in.
You bring it, you just import it in. Same way you brought in the original ThinkCube database, you just don't need to create a new database. You just right click on ThinkCube, go restore, point to that file, and it'll bring in the missing table with the data. Okay. So that's basically the union, the intersect, and the accept. You can have as many of these as you want. By that I mean, you can do union, accept. And the way it works is it goes top to bottom. So it'll do the first two, then apply to the next one, and apply to the next one. Unless, of course, you throw in some brackets, because then it resolves the brackets first, and then builds its way out from there. But it behaves just like every other SQL thing you've ever seen. Like every other piece of math you've ever seen. Any questions about that? Okay. These are handy, but they're not something you use every day. You know, I use them maybe once a year. But it's good to know they exist. Otherwise, you're going to be like some people that didn't know about these that I know, and they wrote themselves some code to do it themselves. That's really efficient, to say the least.
You have to select the same fields.
It has to have the same number of fields, the same data types in each column, and some servers like Postgres care about the name of the field.
Okay.
So that's actually written on the rules behind it. And it'll be part of the video. Okay, now. I hate this. Theory. Just pure theory. And pure theory is not fun. But this stuff does show up on the exam. So, you know, you may want to pay attention. I will be putting this up on Blackboard. I just didn't have a chance because I was running late today. I'll put this up on Blackboard before I leave today. If not, Somebody send me a note and remind me, and I'll put it up.
Do you know if the final exam has been scheduled?
Theoretically, yes. We're still negotiating who's in what room. There's so many students that we're having some logistical issues. Apparently, this is one of the biggest exams the school's had in a long time. Over 450 students. Yeah, we got the gym and the cafeteria, which isn't something that happens very often. And we'll be sending out the announcement probably this week as to when everything's scheduled. Actually, it should show up on comms, not comms, Access. Not yet?
Type that one up.
Okay, it normally does show up on there when the exams get scheduled, so.
I think it's up on Access.
It should be up on Access.
Access.
The final ones came out.
Right? That's where you check it. There's only one, only the successes.
All right. So far, we spent time discussing normalization and how important normalization is about breaking down your data, making it small and compact and hard to break, because the better normalized your database is, the harder it is to break the data that's in it. However, there's times that you have to look at the normalization going, I went too far. Or, holy crap, we got so much data, this query is taking forever to run. Or, why the heck are we doing this? Those are usually the three questions that bring up the concepts of denormalization. So denormalization is the process of transferring normalized relations into non-normalized physical record specifications. Okay, in other words, you take a nice normalized data and you denormalize it. So you're going to take two tables that are related that really don't need to be two separate tables. There's some definite improvements. It makes things go faster. Why? The more joins you have, the more overhead each query runs. But there's always some costs that go with it. Apparently it uses up more database, more table space, like disk space, because you're duplicating data in a couple of places. That means those bytes are eating up more room. There's always the risk of data integrity issues, consistency issues. In other words, if you start duplicating data and you don't write your code to handle all the duplicates, guess what happens? You end up with broken. Now, there's three, and I'll be going through the three common targets. One is one-to-one relationships. Then there's many-to-many, that don't, another is an associative entity. And then there's reference data. And if there's some data that's not used anywhere else. Okay, the first one is the one-to-one. For example, a student has an application and to a school. For example, a lot of schools, when you apply to the school, you apply to the school and then you say, I want to apply to this, this, and this program. You don't apply to just one program, you apply to multiple programs at that school if you want to, whichever only you put in one application. A lot of CIS systems and SIS systems will track student to one application, but they actually have them in separate tables for some unknown reason. Realistically, you can actually collapse it down to one table like they did here. So you got the student and the application would have what date and whether or not they were qualified. And you can actually just collapse it down to one. So the student applied to this campus with those qualifications. It's just one table, that means you don't have to do a join, you pull it up. If a student applies more than once, well, you got different issues. But realistically, this is a good use of denormalization. There's not much else I can say. I was taking a breath to say something else. I don't know if there's something else to say or not. When you get the slides, you'll see there's notes. These slides are from the textbook. And they've got like paragraphs of text under this. This stuff, a lot of this stuff shows up on the exam, just so you know. There's not tons of it, it's just there. All right. The other one is if you got a many-to-many. So you got a vendor and an item. And the way it works is you could get an item from more than one vendor, and the vendor might sell more than one item. Now, what kind of environment would that be in? Manufacturing. This is very common. You know, bolts? They come from more than one manufacturer. Screws come from more than one manufacturer.
Chain management.
Chain management. So what happens here is sometimes you'll send out a quote to all your vendors saying, I need some 3/16 fine thread nuts. Okay, you send it out, they give you a quote coming back. You might have 5 vendors that sell that, but you might also have, that vendor might sell 100 different products, and you might buy 10 from one, 3 from another. This is a many-to-many job. That's what's happening up here. Now this is what it would look like normalized. So you got the vendor and the contact information, you got the item in the description, and then you got the price that was quoted. So it's a nice clean table structure. Realistically, you could just collapse price quote and item into one table and just call it item quote. That's what they did. And the only thing that's unique from all of this is the description. So you throw the description into the price quote and poof, you got 2 tables. The lookups are faster, especially if you're dealing with huge manufacturing chains. Can you imagine what the manufacturing process looks like for, say, a Boeing 747? You know, every single bit and piece gets quoted out to the lowest bidder. And so you'd end up with duplicated descriptions. So there's always a risk that this column gets damaged. Other than that, yeah, that's the only thing that would happen here. That's when you do a many-to-many. I'm not so fond of this because of the risk to the description. This isn't that bad. It's actually not as bad as the one-to-one on the previous example.
Sorry, so getting rid of the associative entity there doesn't break the relations?
No, it doesn't break the relation because what's happening is you take the description here, you put it in there, and you still have the item ID, you have the description and the price, and it's still connected to the vendor. You're just getting rid of the associative entity. You're connecting this one directly to this one by literally taking this to here and this to here. So you're taking these 2 tables, combining them into one. So you just have a many-to-one relation, one-to-many relationship instead of a,
Oh, okay.
you know, a many-to-many.
Thank you.
Yeah.
So how would you have duplicate descriptions?
Well, for example, we got vendor 1 selling a 3/16 nut. We asked vendor 2, 3/16 nut. We have to put that description for every single quote, as opposed to here, where you describe a 3/16 nut, and then you just associate it to the quote instead. That's the risk. This is going to be a heck of a lot faster.
All it takes is a space.
It takes a space. It takes a batch update that suddenly goes wrong. There used to be something that doesn't happen very much anymore. It was called EDI, Electronic Document Interchange, where a file would come in from the vendor and then it would get data processed line by line every day. And at the end of the day, once the EDI was done, the database should be consistent. There's always a risk that you know, there's one bad record in the EDI and the update fails halfway through because there's an extra space, or someone reason there was a little blip in the internet and the file got corrupted on the way there. Or back then, actually, it would have been the dial-up broke. Really, I kid you not. I mean, to give you an example of what I've dealt with this, my second job out of school, and their system ran on a Unix box with dumb terminals, and they actually wrote supply chain management systems, and one of their suppliers made lamps. Another one is Adidas, the shoes and the sweaters, one of their customers, and the supply chain management on that was atrocious. You'd think, you know, it's clothes. Holy crap, there's a lot of little bits and pieces in those shoes. And the rubber and the nylon and the laces and the cotton and all this crap. And one of the issues that happened one night is what would happen, their suppliers, after they sent a quote, could get their management system to do a dial-up. It would actually dial up into their phone number, and then the modem would answer. It'd do the ding dong bong bong bit. And then it'd send a stream of data, and then suddenly there'd be like a thunderstorm. There was a thunderstorm rolling through. So I think, if I remember, one was in Texas and one was in Michigan. There was a thunderstorm running through the middle, and there was static on the line. One of the records got mangled. So they had to handle this, because they actually had this layout, not that layout. It became this layout after that. But that's, you know, the risk of this. Nowadays, it's not as common because everything has checksums and all kinds of stuff in it, but, you know. Okay, now the next one is reference data, where You have instructions for an item, right? Same instruction can be used for multiple items. You store a 3/16 nuts the same way as you would a 1/2-inch nut. Instructions: put in box, put box on shelf. And theoretically, for each item, you could denormalize it so that each item is actually has a full description of where it goes and all that, as they did here. Honestly, this is a perfectly valid use of that, because really, most of the time, you might have 3/16 nuts, so it's not going to go in the same bin as the 1/2-inch nut. Therefore, it'll probably be in one slot over, 2 slots over. That's the other purpose for denormalization, is that. Now, denormalize with caution, because the warnings come with it. When you denormalize, there's the chance of error and inconsistencies. I give you guys a couple of examples. It can bring back anomalies. Update, insert, delete anomalies. For example, you got a single record that describes a 3/16 nut, and you delete that record. Your system doesn't know what a 3/16 nut is anymore. Gone. You force reprogramming when the rules change. That one's actually not a very valid risk, because guess what happens? You change the table structure, your programming changes to match the table structure anyways. But if you decide to denormalize your data, you may have to rewrite your application. Those bits that talk to those tables, because obviously you've changed the underlying structure. All right, there's other ways you can improve the performance of that. And you change the organization, which I'll be talking about in a bit, or you change your queries so they're better written. Like anything else, queries can be optimized. You can write your queries so they run a little bit better. An example of that I've had was at one point I was writing a query that was querying millions of rows, and it was summarizing this data. And one day before I went for lunch on a Friday, I started the query to see how long it was going to take to run. I came back from lunch 3 beers later, so it was a really long lunch break, and it was still running. I'm like, well, this sucks. So that was done for that project for the day. So then the next Monday, as I was taking a walk around the War Memorial, it hit me what to do. I broke it into 2 queries. It ran in 3.5 minutes because I changed how I thought about the data. There's always optimization. Sometimes actually making it more than 1 query is actually more efficient than trying to do it all as once. Right? How many of you have tried to carry a fully assembled piece of furniture up a flight of stairs? As opposed to, I don't know, buying the box from IKEA, carry the box and assemble it in the room it's going in, or you assemble it in your living room, then you discover it doesn't make the turn in the landing, right? That's the difference between normalization and denormalizing your data, is that. Now, these slides don't talk about one last purpose of denormalizing your data, and that's called data warehousing. For example, do you think Amazon runs queries on its live data every single day? They want to know which products sold the best this week, or they notice that, the grommets aren't selling as fast as the widgets for some unknown reason. So they said, well, maybe next week we'll do a 5% sale on all the grommets. They need to do stats. So what happens is they create denormalized rows of data where it would be, on this date, this many of this was sold. And they actually run queries and denormalize the data so the descriptions are right next to the price, are right next to the volume and that kind of stuff. And it goes into a separate database. So it denormalizes the data and stores it somewhere else for data warehousing purposes. That's part of business intelligence. So I don't know if CT has a BI. I think it's actually an optional you guys have later, I'm not sure. But BI, that's part of BI, is learning how to take the data, break it down into denormalized data sets that you can query quickly to do large volume sets. Really quick. All right. And this is where my lecture fell apart on Monday. Why? Because it's not a topic I work with very often, so it's not as fresh in my brain. Partitioning. Now, those of us that are past a certain age remember when Windows and DOS couldn't access larger sizes of disks. Actually, it was actually not the disk itself they couldn't read, it was the partitions. There was a limit of how big the partition could be. So you take your big disk that you spent hundreds of dollars on, I remember my first gigabyte disk, my first 1 gigabyte disk cost me $500. And then it died 3 weeks later, it's defective. It sucked. I discovered that DOS 6.1 didn't understand that. So I had to partition it in 250 meg chunks. Anyways, I might as well have had 3 drives on my machine in the end. It would have cost me less. But that's partitioning in the old days. You can do something similar with the database with your data inside the database. Now there's 2 kinds of partitioning. There's horizontal and vertical partitioning. Now, horizontal partitioning means that you are taking the tables and you're breaking it into subsets. Oracle can do this automatically. Postgres can sort of do it if you plan your data properly. Essentially what happens is you can set it up so you can set a date range so that data that's more than 2 years old goes into its own table. You can actually search across all the partitions if your database server understands it. But the current data is in a fast access area. The older stuff is in a slow access area so that it's archived and you only go in there when you need to. You can arrange this so that it's broken down, that each partition goes into its own location. This is actually an Oracle thing. I usually try to stay away from implementation specifics, but this is why people still spend money on things like Oracle. And DB2 does this also. The higher end products from Sybase, what used to be Sybase, which is now SAP, do this also. Microsoft SQL Server is trying really hard. They're not quite there yet. With Postgres, there's a way of doing it by cheating. You create something called a table space, which I think is actually covered later in these slides. And so what happens is you can create partition, then say partition A, which is the current active partition, is on the SSD, and then partitions B is on a spin disk, and partition C is on a really slow spin disk. So you can actually separate the performance depending on what needs to be queried. Obviously, if it needs to reach across all 3 partitions, it's getting slower. There's some challenges to that, and I'm actually going to cover that a little bit more. The other one is vertical partitioning, where you take a big table and you break it down into slices. Instead of being slices of rows, it's slices of columns. So this is a good way of protecting your data. You could have the common customer information in table A, name, phone number, address, blah, 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 blah. In table B, you could have their credit card information that's safely secured in a different table space or even on a different server, where you're taking the data and you're breaking it across multiple locations just to protect it. That means that you can give your users permission to see table A, no problem, but only a subset of users can see table B, because they're not allowed to look at it. The built-in security that you define stops end users from seeing the subtables, the separate tables. What happens is you have to use the same primary key in each table. So you've got basically table A ID, table B ID, table C ID, like the naming conventions have been using. But what happens in table A, if the ID is 5, in table B it's also 5, in table C it's also 5. The primary key is the same in all 3 tables. They use the same sequence for all of them. And normally when you start writing the data, it starts with A, then writes to B, then writes to C, so that it snowballs and rolls down that way. It's sort of like, if I want to use this room as an example, partition A, partition B, partition C, right? Partition A has fast access, although that one's sleeping. Partition B, they're a little bit slower. Partition C, nobody's paying attention, right? So I actually got to get your attention. I have to actually ask you to pay attention, whereas you guys should be paying attention instantly. So I picked the one that was asleep too. So you're never going to live it down now. And then there's these guys here who are more or less paying attention. They're a little bit quicker than these guys. But you're all in the same room. It's just you've been broken down into 3 separate pieces. You all contain a separate set of information. You guys contain customer information. You guys maybe contain credit card information, and you guys contain archived orders or something. Not orders, but something else that you don't normally update very often. Maybe preferences, for example, would be a good partition. Or maybe that's something that changes once a month or once every 6 months. Whereas that's something that changes daily, and that can be something that changes, every couple of weeks kind of thing. You can divide the data that way. And now, of course, you can do the good old combo, right? Slice and dice in both directions, which is a combination horizontal and vertical. Now, both of these require programming changes to your code, obviously. This one has to understand the concept of how it's broken down this way. This one has to understand how it's broken down this way. Towards the end of the term, I'm going to talk about some of the ways to get around this. It's kind of gross, but there's ways of getting around it. Okay, advantages of partitioning, because there's always good and bad with everything. And it's sort of, there's big advantages and disadvantages to everything. Advantages. When you partition, it improves the efficiency. Ooh. That was cool. That was my laptop deciding it needed to resync. Advantages of partitioning, efficiency. Okay, records that are used together tend to be grouped together. That means all these guys are all grouped together, they'd work well together. Whereas if they need to talk to these guys, well, it's going to take a little longer because they're across the room. Local optimization. I can actually optimize each of you to have different access. I can say, hey, partition A, you guys are going to sit in a little cluster, you're all going to be touching hips, so you can talk fast. You guys in partition C get to have lazy boys. You're all spread out because you don't need to go very fast. The communication doesn't need to happen as fast. Because we don't need to talk to you very often. Therefore, if I say, hey, by the way, I need this information, let me get it on my chair, and I'll come and give it to you. Whereas these guys can say, well, hang on, I got less information, and they can just go quickly. Security. I can put up a wall here so that anybody who can see this can't see these guys. That's the security. I can divide it, slice and dice it. Load balancing. So I can take the partitions, put them on different disks. That means you can stream your reading and your writing from multiple disks at the same time. For example, you put customers on one table in one space, or you put the raw customer information on one and the credit card information on another. So if I go select star from customer and have them allowed to see both sets, two disks are going to give me the information at the same time. That means that the return is faster because I'm distributing across multiple lines of I/O. I don't know if they've talked to you guys about I/O yet or not, but I/O sucks, right? Your pipe is this big, and the more you try to get through that pipe, the less gets through because it's just like a bathtub when you pull the plug, right? It just doesn't disappear. It's all got to take its time or turn going down the hole. Database is the same time, the same trick. The trick is though when you use different disks for your data, is we pull the plug up, two different plugs at the same time. That means the water drains twice as fast because it's going to two different places. There are issues. Inconsistent access speed. You guys are fast because you're touching hips. These guys are slow because they got to get out of the lazy boy, right? These guys are on an old 5400 RPM, lasts forever hard drive. You guys are an NVMe, PCI Express hard drive, like that. And these guys are, eventually show up to the party. That's the issue. Then what happens then is the database server has to know that it's dealing with really fast people and really slow people at the same time, and it's got to basically wait and know that it has to wait to get the data. Complexity. Partitioning is non-transparent unless there are ways of making it transparent. But it's not transparent initially. In other words, it's broken down in separate rooms. That means that it's obvious that it's broken down. For the programmers, it's challenging. And there's always the case of some duplicated data, right? The primary key is shared in all three. That means that the primary key data gets copied to all three sets. It means they're duplicating the primary key into different partitions, depending if you did a horizontal or a vertical. If you're doing a vertical, the primary key is copied in each place. If you're doing a horizontal, you get less duplicated data, but it's broken down in further places. All right, Oracle's partitioning. Like I said, I try not to be too specific, but a lot of the other database servers implement at least one of these. Oracle just so happens to have all of them. They got a range. 2013 to 2014. 2014 to 2015, that's a range. You can partition by date. However, you could end up with an imbalanced distribution of rows. If I use an example in here, I could go with, what year were you born? Those of us at a certain end of the scale are going to be pretty much by ourselves. Right? Anybody, 1970s and before? Or 1985 and before? How many of that in here, 1985 and before? Woohoo! Look at that. Okay. How many of you in here would have been born 18 years ago, roughly? 18 to 20 years ago. 1, 2, there we go. See, uneven distribution of data. Then if I go 18 to 21, okay, now I go 21 to 30 years. There we go. See, that's even more uneven. But that's the uneven distribution of data. So this one, I wish I could take the camera and turn it around really fast, so that if somebody's watching this remotely, they're going to know the percentage. That's pretty bad. I had to go add from 70 to 85 because I was going to have like 2 of us in here at one point. Okay, hash partitioning. Hash partitioning, what it does is it takes a fingerprint of the row of data, and then it separates it based on that on a part of that fingerprint. That means that the rows get distributed evenly amongst all the bins. However, then you can end up with some really strange range of values where some of the data is totally unrelated to other. So if you try to do a select star from customers where city is equal to Ottawa, I might end up with 20 in here, 3 in there, and 40 in that pile. So you end up with uneven distributions that way. But I might end up with 100, 100, and 100. Why? Because that's its purpose, is to make sure it's balanced evenly. List. I just thought, yeah.
How does the hash function work?
Well, it does a fingerprint. So back in the day, you had something called the CRC32. That was one of the first hashes out there. It gave you, what, a 4-digit number, if I remember right? 3-digit number? And that number basically identified a fingerprint. A little bit later, some other ones showed up at the party, MD5. MD5 is a common hash. People should never use this to store passwords anymore, because every combination has been figured out now. But MD5 is still used often for transmitting files, because you run an MD5 hash on a string, it gives you a fingerprint that uniquely identifies that string. And what it does, it'll take, for example, maybe the first 10 characters of that hash, and it'll separate folders. I actually have written something like that for files, where I run an MD5 on the file, grab the first 10 characters of MD5, and I start creating folders based on the first 10 characters of that. So that as files come up, if they have the same one, it distributes them into each of the bins based on that. So for example, I could go with anybody who's, let's pretend your name is a hash. Anybody whose name starts with A, go over here. Anybody whose name starts with B, go over here. And that's what the hash does. But it uses a fingerprint instead.
But it's a randomly sorted, or is there?
It'll end up being partial random, as in, if I run a hash on your first name, it'll be completely different than a hash on his first name, but you might have the first same 3 characters in the hash. That means if I decide to use the first 3 characters of the hash rule, you'd both end up in the same bin. Whereas the ones behind you might end up with 3 separate bins, because that's how the hash worked out. You end up, it usually ensures that it breaks down pretty evenly, but there's always, a little bit of overlap. Lists. Canada goes here. Trump Tower goes here. England goes here. I can create specific lists, and you can divide the data by lists. It's not the best way of doing it, unless you're trying to arrange the data so it's fast access depending on what country you're in. For example, if some people have distributed databases that are actually running on Amazon, and they have multiple instances of this database, and they actually have the data broken down by country where the instance is residing. So North American customers, because there's no Amazon instance in Canada, we could actually say, okay, anybody in Ontario, Quebec, and East end up in the North Carolina data center. Everybody west of Ontario ends up in the California data center. Why? Because there's less pipe. I love using a pipe because it's the worst example ever, but there's less pipe work between you and your data. Therefore, that's what list does. You can break it down by specific lists. Then you have to create a new list. Like, for example, when a country like Yugoslavia explodes into 3 to 4 countries, and therefore suddenly that one list needs to be broken down to 3, unless you want to keep them all in the same bin. And then there's the composite, where you grab one or two of the other kinds, a range plus a hash. This is when you have huge amounts of data. For example, banks, the government, whatever government you want to talk about. They have tons of data, and they'll use range and hash partitioning, or they'll use range and list partitioning as applicable. Actually, usually what banks will do, they usually do a combination of list and range. For the few bank DBAs I've spoken to, although they're very cagey about when they start answering questions about things like this, because they don't want to admit how bad or how good their databases are. But they tend to use a combination of list and range. The range is often the date of your transactions. When did things happen in your account? The list is usually broken down by your branch. Those of you that remember, know how to read a check. You've got an institution number, which is irrelevant, but the branch number helps break down your data to what is relevant to you, and then you have a range of transactions. And the older the data gets, it gets pushed back into the archives further and further. That's why most of us can't get more. I know BMO gives me 3 years of transactions I can pull back. Any more than that, I have to go to a branch and ask. And then they log into this really old, dead, dumb terminal, because the one at the front can't do it. You have to go see a manager. Because you want to argue the fact that 8 years ago you finished paying something off, and suddenly it shows up in your credit report you didn't pay it. So you got to go pull it out of the old records. Vertical partitioning. So that means you're taking the columns of the table and you're breaking it out across multiple bins. And this one, I already explained this fairly well, but you could take one part table, and by part they mean like parts, car parts, and you could have a section for accounting, a section for engineering, and one for sales. In other words, the sales guys need to know certain things about it, the engineering guys need to know something else about it, and the bean counters only care about how much it costs, or how much it's worth. Right? So the data, they'd have the same product ID in all three bins, but the accountants would have this is how much it costs, this is the depreciation rate, this is how much we sell it for. The engineer guys would care, is it made out of nickel, is it made out of iron, is it made out of this? What are the exact, precision pieces? And then the sales guys say, it's chrome.
Shiny.
That's shiny. You want this nut because it's a little more shiny than our competitor's nut, but it's also made out of chrome. But we have a special polishing process that makes it shinier. As you can see, I have a really hard time with sales reps. One of the advantages of this is that it reduces the relation on each one. That means you don't have one global parts table that's constantly being hammered. It breaks down the data into smaller chunks so that each individual subunit can grab those. Problem is, though, when you need information from, let's say, you're going to run a query, and say in accounting, it costs this. So this nut costs us 3 cents. The sales guy knows we can sell it for 50 cents. So in the sales book, it would show the list price is 50. The cost price is 3. We want to know what the price differential is. So we go, price of the sell price minus the cost price is our profit margin on the given product. Assuming this labor is not a factor. To be able to calculate that, you need the accounting and the sales tables. Then you have to use a join to connect the two tables together to get all that information out. This is for performance tuning. All right, any questions about partitioning before I keep trucking? It's, it's what it is what it is. Just make sure you read those sections of chapter 5 for the hybrid and the test. That's all I got to say about
Are
it.
we going to be doing this in any of our labs?
No. No, because I didn't know I was teaching this before the start of the term. So I have no course material prepared for this. Just putting it totally honest. And honestly, I can't even give you guys data sets big enough for it to make a difference. I mean, yeah, I could create a database for you guys that has enough data in it for you guys to feel the performance difference if I did it. I don't know if you guys want to start loading 2 gigabyte, 3 gigabyte files on your computer just to run a query. And then the query takes 10 minutes to run, as opposed to 9 minutes. This is theory. Exactly. I've had to deal with this once in the last 20 years. But the concept's important that you know that it exists. That's because I don't deal with large data sets very much. Okay, physical database files. Now, when you are talking about, so far we've been talking about the virtual concept, right? This is a table, it's sitting in some numeric little place in the computer does magic and stuff happens in memory. However, when you turn off the computer, the data doesn't go away, right? Hopefully it doesn't go away. That means it's stored somewhere on a disk. That means there's a physical file behind all that data. And essentially, when the database server loads up at first, it does the first table scan, it actually reads the table and loads the most commonly used records up in memory. And it stores up in memory. That's why database servers love lots of RAM. Why? Because they can store as much of the database in RAM, because RAM is fast. What happens though, there is a physical disk where this data needs to be written. Now, by default, Postgres creates all of it. I'll use Postgres as an example, this is the one you guys are using. All the database files are written in one place. MySQL, all the database files are written in one place. Same thing with everybody else. However, some database servers, Oracle, Microsoft SQL Server, Postgres, and some of the other big, DB2 for example, the big boys, allow you to create something called a table space. The table space is cool. What you can say is, this table space is allocated to a certain disk. So you can create a table space and say it's on disk A, which is a PCI Express hard drive that is insanely fast. 3,000, 3 gigabyte reads and 2,200, writes. Insanely fast disks. And then you could have the archive stuff sitting on an old high reliability 5400 RPM drive in an old RAID array. And you can say table space fast is here, table space slow is there. So when you create your tables, you can actually, in Postgres for example, you can say this table goes into table space fast. So when it starts creating the physical files on the disk, it'll actually put the files on the different faster drives in different locations. It's pretty cool. There's some things. So there's a segment. A segment is it a table, index, or partition? What a lot of people have started doing is they'll actually use a RAM disk. Now, most of you are too young to remember this. There once was a time where our hard drives were so slow that we actually dedicated part of our little 8 megabytes of RAM to hold DOS, so that the commands ran a little faster. So what would happen is when the computer first booted up, it would actually create a temporary partition in memory and copy the files into it. It's old technology.
Like when? How long ago was that?
My first PC was a 386DX40, and it was getting out of style at the time. It had 8 megabytes of RAM.
Like early 90s.
10 gig,
1989 in my case.
10 meg hard drive.
10 megabyte hard drives.
Okay.
Yeah. So back then, the hard drive interfaces were so slow that it was actually worthwhile to spend the extra 5 minutes at boot up, copying everything into memory, so that when you ran some commands, it ran pretty spiffy. Database servers have started doing the same thing now, where they'll take some of these segments and store them in high-speed memory or on a high-speed disk. The PCI Express hard drives, or the new M2 drives, for example, the new Samsung 960s, are blazingly fast. Like we're talking 3,300 megabyte per second. So that's 3 gigabyte a second reads and 2 gigabyte a second writes. That's actually faster than the computer can compute. So they'll store stuff like indexes on those kinds of drives. Why? Because index scans are expensive. And if it can read through that index really, really fast, the query is going to happen faster. Or you can choose to do contiguous length or data blocks. You can choose to take the smallest units and put it on the fastest disk, the one that doesn't have a platter and an arm, so that it needs to read up little pieces, it just reaches into the disk and pulls them out. That's what that's for. All right. Hey?
Shipped orders, unshipped orders.
Yep. Bins. So there's some techniques for physically arranging your records. You decide whether or not it should be fast retrieval, efficient storage, because certain kinds of disks take up more room than others. Accommodating growth. There's different kinds you can choose and how to organize on different disks. I'm not going into a lot of detail on this because really it's just terminology. But yeah, this does make a difference. So sequential file organization is the fastest to scan from A to Z because it literally goes from A to Z. There's a problem though. When it's sequential and I need to insert something here, it rewrites the entire file. Sequential files are really slow for writing, but they're really fast for going through from start to end because it knows where to jump. Indexes. Okay. Indexes break down in A.
We haven't talked about
I know. That's what I'm talking about right now. I'm going to be actually talking about creating indexes and stuff later. What am I doing for time? Oh, crap, I'm almost done. One at a time. Okay. Index organization is interesting. It's breaking down the list based on values. And the most common database index is known as a B tree, a binary tree. And the way it works is something like this. Let's say I got values A, B, C, D, E, and F. And the way the binary tree works is it'll take those values and divide it in two. Suddenly we got A to C and D to F into two separate piles. Then what it'll do is it'll take that and divide it further. And it usually tries to keep even numbers, so it can keep dividing by 2. Which my example is not too handy for that, but we'll go with it anyways. So in theory here we could have A, actually we'll divide it by 3, B, C, D, E, and F. So normally when you do a sequential file, let's say in a sequential file I want to find F, and I literally got to go from A, B, C, D, E, F to get to it. But when I use a B tree index like this, it'll go, okay, I'm looking for E. Is E between A and C? No. It's between D and F. It'll go down this branch. Then it'll go down the next branch and down the next branch. So basically, it is the size of the table divided by 2, eventually, to get to the right bin. In other words, you're speeding up the queries by 2, by a factor of 2. So what happens in the end is it depends on the depth of the tree, not the breadth of the tree. So if we happen to have an index and it's breaking down numbers instead, so 1 to 1,000, 1,000 to 2,000, and it's breaking down by the next set of digits, 1,000, then it's broken down by hundreds, and then by tens, it'll go down the tree really fast because it only has 3 jumps, whereas if I had to do a sequential scan to get to, 1,355, you would have to go through 1,355 records to check if it's there. Otherwise, you'd need to do 3 lookups to get to, the smallest common group. That's what indexes do. Actually, in the later lecture, I'll actually do to create the index and stuff. But this is the concept behind it. This slide just talks about indexing joins. In other words, if you got points of commonality between 2 tables, create an index on it. That way the lookups are faster. That's all this is trying to say.
So foreign keys?
Yeah, always index your foreign keys so the lookups are fast. If you don't index your foreign keys, like for example, Postgres automatically creates your foreign key indexes when you create a relationship. MySQL does not. Actually, half the time MySQL doesn't even create the relationship properly. And then there's the hashing algorithm, which comes back to what I was talking about the files earlier, where it takes the value in the index and stores a part of it. So then it just needs to sort through the hash to find the place. And actually, commonly, what happens is it uses most database servers use a combination of the B tree and the hash. So for example, you're searching on a person's name, And you're not just searching on, Dan. That field happens to contain the entire record. So, for some people, you still only have 2 names. And if you come from Puerto Rico, you have like 8 names. Why? Because that's just what that culture does. You just keep accumulating names the more down the family tree you get. Therefore, that's a really long piece of text to index. So what it'll do is actually create a hash of that and then create the B tree based on the hash. So anything that starts with A goes in this bin, anything that starts with B goes in this bin. Then it goes, okay, when if the next character is 3, it breaks down the bins on each of the characters. So it creates a bin based on each subset of characters.
Is that for the query? Or
No, it does it automatically in the background.
Okay.
Then the index speeds up your queries by creating these structures that it can search through really fast.
That's when you're populating the database.
And when you populate the database, there's a little process happening in the background, hashing up your data and adding to the indexes so you can search faster.
So in this case, only for the complicated names or for every single?
Every single name, whether it's long or not, it's going to hash it. Why? Because it has to. Yeah, it's something you don't see. It's magic in the background. In Oracle, you can actually go and muck around in the indexes manually. That's not a good thing to try to do, unless you're a rocket scientist or you got more PhDs than a tree has leaves. But you can control it by setting some parameters at the server level, way above the pay grade of this course. The CP students take this in their 4th term, and they only have 4 terms. This is a quick table that explains the advantages of each of the kinds of file organization, whether it's sequential indexed or hashed. And you should just review it. So when I put up the slides, just read through it. There's also clustering. That means that you can arrange certain files that are related, certain tables that are related to each other, sit next to each other on the disk. Not so common anymore because of the SSDs. Solid state drives don't have this problem. But for those of us that remember back in the day when we used to defragment our drives and put all the important files on the outside edge of the disk, because the outside of the disk moves faster, so we'd read faster. That's, those of us, I think the 6 of us in the room that remember this, laugh. Everybody's going with, I have no idea what he's talking about. Back in the day, clustering was common that you'd put the commonly accessed files on the outside edge of the disk, and you'd actually arrange it that way so that the records that are related to each other would be read at the same time. So customers and addresses would be stored side by side on the disk so that the head doesn't need to move as much. Therefore, it improves read times. Nowadays, with our SSDs, it makes absolutely no difference what the data is. None.
As opposed to partitioning where you're placing them on physically different.
Or you could arrange your partition. You'd actually create your computer with the partitions on the hard disk, saying that fast partition would be track 0 was the inside, whatever the outer track was, the outer sectors, and you'd allocate 500 megs to the outside, and you'd create a table space that would map to that partition, so that all the important tables get written into that space on the disk, so that when it's spinning faster. Because the faster the outside edge, the angular momentum, there's a piece of physics terminology, the angular momentum on the outside edge is faster, so that means the data gets read faster.
How are clustering and partitioning different?
Yeah, the partitioning, you partition the disk, and then you cluster the files in each of the partitions.
So they go together?
You could use them independently or together. Depending as your database grows, it gets more and more important. Now that everybody's moving to cloud services, this is becoming less and less important. Why? Because the workloads separate across multiple computers and multiple disks.
But you would still have clustering and partitioning wherever they are stored.
Theoretically, yes. But if you're using something like Amazon Data Services, you have no control. So you're using a homegrown Blade cloud setup. You bought a couple of Blade servers, and you're running a cloud across all the blades. You don't get to control where things happen anymore. Each of the blades is responsible for its own workload, and it's the clustering software that takes care of managing, make sure the workload works right. Oh, actually, there's the syntax for creating the indexes. We're almost done, actually. 2 more slides. Creating a unique index, normally done on primary keys. That means that value can only be in there once. Often I've seen people create multiple unique indexes. The primary key is always unique. However, they might want to make sure that email addresses or usernames are unique. And you can create a unique index on a username. That does two things. It speeds up lookups on usernames, and it makes sure that you can't put in a duplicate value. That's what the unique does. Then you've got non-unique ones, which are often used for phone numbers, product codes, well, zip codes in this case.
Is this similar to making a constraint?
No. This is like a constraint, similar to constraint, but not. This is just raw performance. Yeah, this is similar to constraint. You're creating a unique constraint. You create a unique index, the same thing as creating a unique constraint. It's
So
the same
next
thing.
time I try put in a duplicated email value,
It'll
it's gonna
bark.
reject it.
Yeah. And then the non-unique is used just for fast lookup. That's its purpose, speed up queries. Okay, rules for using indexes. Use them on larger tables. Duh. Tables that have less than 1,000 rows is not worth creating an index on. All you're doing is using up disk space for nothing. Because for usually the math for an index is roughly, for every index is 25% of the source table space. So if the original table is of 1 megabyte, the index will be 250K. So suddenly if you have 5 indexes, your indexes actually take up more room than the source table. Indexes do come with an Achilles heel. Always index the primary key. Duh. Index search fields. Anything that's used commonly in a where clause. In other words, if you search where city equal to this, probably want to index the cities. Why? So you can find the cities faster. Anything that you put in an order by or group by. Why? Because it makes the server sort things faster. You should always index when there's more than 100 values, but never when there's less than 30. I don't know what you're supposed to do with 31 to 99. That's a judgment call at that point. Essentially, if you got more than 100 values, it's probably worth indexing, depending on how much volume your database server gets. All right.
What's the value in that case? Is it an instance or number of columns you have?
No, it's just sheer the number of rows.
Number of rows.
They're not talking number of columns, they're talking the number of rows. This is the last slide, guys. All right. Avoid the use for indexes on fields that have long values. Like we're talking like text fields that have like, a megabyte of text. Don't index that. That's just bad. It just takes up room for nothing, and it's not going to give you any performance gains. It's like, that guy who's trying to get gains, but all he's eating is Big Macs. It's just fat. For example, if the key to index is used to determine location of a record, this isn't something you see in most database servers. This is actually an Oracle thing, where you can actually physically locate the record on the disk in Oracle. You actually run a query that tells you physically what sector that piece of data is in. Don't use that to index. Use, like a surrogate data, like a sequence. Like, how Postgres uses a sequence to count the records, 1, 2, 3, 4, 5. And Oracle does the same thing. Use that. Don't use the actual record address. Because you know what might happen? If your server shits the bed, and you got to reload your database, all those values are going to change. There could be a limit of how many indexes per table, or how much space each one has. You have to check the documentation. There's always limits. Contrary to what your parents tell you, there's always limits. And then there's a few things. Nulls. Don't index stuff that has nulls. Why? As far as the index is concerned, that record doesn't even exist. That means that unless you search through a record, and it's an indexed value, but some of them are null. What's going to happen is it's actually going to have to search through everything that has in the index. So I didn't find anything. Now I'm going to do a full table scan. Therefore, now you're doing 2 lookups instead of 1, because you happen to be searching on an index that has nulls in it.
So should your index not have any nulls at all?
That's what it's saying. You should not. You should try to create your indexes so that you index on stuff that never will have a null, like your ID, or maybe if you make sure that your username is not null. Therefore, you want to index the username, especially on a users table, so you can do that login a little quicker, or you need to look up the user a little faster by name. That's when you index. You don't index on the last time they logged in because who cares? Okay, boys and girls, that's where we're at. I am still in communication with the other profs in regards to the labs and tying down the last bits of everything else. Pay attention to more announcements coming. I'm trying to keep everybody in the loop as much as I can. The good news is I see Howard every Monday. And Kamari about gave me a heart attack last week. So I was answering Sue's question. I turned around and Kamari was standing right here. I'm like, whoa, I almost ran over her. So we're communicating, we're almost now, all the lab monitors and us are almost all on the same page. It's still a little painful for everybody, we understand that, but we're doing our best as we can with the circumstances. Hey, I'm just going to kill my recording and then